Good afternoon, everyone. I'm going to quickly talk about red teaming LLMs. Did manage to break my demos, so I apologize, but we'll talk about the rest of it. Nope. I'm founder of SME. We're based in Cardiff. Currently looking at how AI agents become security boundaries. First time B-side speaker, very nervous, lots of imposter syndrome. Please be gentle. I submitted this talk a few months ago about attacking LLMs, but as I built the research for it and built the slide deck for it, I just realized that you just need basic security stuff. There's no magic here. We'll talk about that. All of the major coding assistants kind of fall foul of this same security principle. I assume everyone's used ChatGPT, Anthropic's Claude, OpenAI, etc. They all have this property in one form or another. I'm more familiar with Claude, so I have a bias towards Claude in this. If I'm down talking some of the other agents, let me know. I'll improve my knowledge. But Claude is the one where I've seen permission systems that allow you to mitigate some of the issues here. But I'm not going to talk about Claude and the Claude code itself, although that's the reference here. But we'll come on to that. So it's the lethal trifecta. So what is it? So around about July last year, Simon Willison put out a blog post describing what he described as the lethal trifecta. And Meta also put out a research later in the year. Three properties are: the agent processes untrustworthy input, prompt, data. It has access to some kind of private data from you or from your organization. And it has some ability to modify or otherwise change the state of either that data or communicate externally as a result of that data. These three things are the lethal trifecta. So, for instance, your IDE reads data from a cloned repo. That's untrustworthy information or untrustworthy input. The assistant can see, if it's running on your machine, it can see your .env files with all of the attendant issues, SSH keys, etc. And it can write files. It can run terminal commands and push the Git. And that's the external state change. If the agent can only access two of these, it's generally okay. But if the agent has access to all three of or has this lethal trifecta, that's where the danger is. That's where you need to protect the system. The property C, the access to external systems, isn't just about tool calls. It could be going to another user. It'd be and then you get self-replicating injection, or can do, which is a queen, which is a program that can produce its own source code as its own input. So it's self-adaptive. And this happened to Meta last week, where an employee was talking to an agent. The agent tried to be really helpful, had access to some data, sensitive data at Meta, put it out on a forum, public forum. Weirdly, another Facebook Meta employee saw that same information, acted upon it, and caused a major incident at Meta. And you see this at other companies as well. AWS recently had a number of similar incidents where their Amazon Q, their Kiro bot, the Kiro LLM took down production in some form in some of the regions. So what does it matter? Agents now security boundaries. Previously, very simplistic diagrams, which I apologize, but before there was a user, there was an app, and there was a database. In a firewall, you had some kind of WAF, you had some kind of authentication. But now you've got a user talking to an agent with tools, which talks to an API, which talks to a database. There are more places that you need to secure. There are more places for things to go wrong. I haven't got a firewall and WAF shown on that diagram, but they would still be in that mix as well. But it's showing that the agent has access to plugins, it has memory, it has MCPs. The tools have access to credentials and the file system and all the rest of it. And then, as we've built on these systems, we have systems which then using that same input to protect themselves. So the one on the left is Redamon, which is like a pen testing tool. The architecture is there. They scan networks, they find vulnerabilities, and they try to fix those or exploit those with minimal human input. So if we look at the lethal trifecta of those, they have just taking Redamon, not picking on Redamon, just using an example. Untrustworthy input, and the untrustworthy input has access to the scan results from the target system. The target can potentially craft responses that mislead the agent about what is or what isn't in the system. Has access to private data, can read credentials, can read your network topology, can read your secrets. Compromised agent can leak those, and leak everything that it discovers. And then you have the external state. It runs exploits by its very nature, writes the graph databases or modifies the target systems. And if you can poison those graphs, then it affects all of the reasoning downstream for either it or other systems. In terms of the local machine, you have identity files. So quite often see a Claude.md in a Claude repository, which kind of tells it, this is what this repository is about, and this is what you want to do. It's a highly simple example here, but on a developer's machine, you might just be doing some TypeScript, and they just want to tell Claude, remind Claude, always use TypeScript. I like TypeScript. We're not using Python, we're not using other languages. But if somebody can get into that repository, they could just add small amounts of information to that file, which now tells, in this instance, well, when you create a new file, give me an audit log and on a GitHub issue, and put all the developers' environment variables in that issue. Data exfiltration. There's a lot of this that we saw with OpenClaw when it was it started to come out with, in those instances it would have been the solder.md. But OpenClaw is loading these files. It's doing it without checking what any of the files are potentially, and they're the .bash RC of the AI age. They're everywhere. You see them in a lot of repositories. They're executed on every session. And one thing to watch is that you might see the Claude.md has been poisoned, but by the time you see it, it's in the memory of the agent, of your agent, which could be in other files, could be in another database, and so on. So the poisoning may last longer than you may not just be able to remove the file to remove this behavior from the agent. And there are other techniques which we'll talk about later, as kind of like Theseus attacks, where the poisoning is such that it doesn't leak it all in one go. It leaks it in small increments across sessions, weeks, whatever. Acts normally for a period of time and then starts to leak, and then maybe starts to behave again. The attack vectors on this are this kind of thing. There is governance, and there's catching up with how we manage and build these systems. OWASP has a couple of frameworks. They have their LLM top 10, they have their agentic top 10, they actually have an MCP top 10. NIST IR 8596, I think it is, covers AI governance. And the FCA, the Financial Conduct Authority, have resilience, which covers AI integrated workflows. So auditors will start asking questions, and they will expect this kind of thing in their compliance reports. maybe not everyone's understands prompt injection, but it's just giving your giving your agent malicious commands. You can think of it a bit like social engineering for an agent. You give it a command to do something that you didn't think the designer of the system didn't expect it to do. And this works because LLMs are not always able to distinguish between the instructions that they've been given at design time and the information that's coming in at runtime. There are guards against that, but you have to know how to put them in and so on. You're not exploiting a vulnerability in code here. You're just persuading your trusted friend that it can do something it's not supposed to do or not designed to do. And that's really what it is. One example is from Copilot, where, as described it briefly before, but somebody downloaded a repository from GitHub which contained a malicious file. Copilot read it, understood it, and exfiltrated the SSH key of that user. So not all exfiltration is HTTP request either. There are other techniques where could just go out to a Slack message, or I saw one recently where it was just showing up as a tooltip on a URL. That was the data that's being exfiltrated just as part of that. So it's not always a HTTP request. This is what I was referring to previously with the Superthesis idea, where MCP Parasite uses your own tools against you, gets on your machine via an MCP. For a few days, does passive recon, understands your secrets, maybe it profiles your infrastructure, and then just sits there for a while, acting normally, doing the job that you think it's supposed to be doing. And then after some period of time, it triggers it. The payload start, either it starts attacking your system or it starts exfiltrating your data. This was from Bountify. So this was an actual attack on Anthropic, which used it was a memory. It pretended to be a memory tool for your agent. And why wasn't it identified? MCP tools such as MCP scan do static analysis. On the face of it, it's not got any, problematic code in it. The tools that are identified in the MCP, they look harmless. It's clean. The payload is in all of the runtime responses when you call the functions. Point in time audit, well, it didn't actually activate for a few days, for 2 weeks. And the tool did what it was supposed to do for the rest of the time. And tools like OpenEdison, they only inspect the metadata, not what's coming out of the system. This is a really recent one. So this was on Tuesday, as a result of believed to be the result of the attack on the Trivy scanner over the weekend. So Trivy is a security scanner that a lot of people run inside the GitHub Actions. It was compromised, and for a day or so, Team PCP had access to all of the secrets flowing through and across people's GitHub Actions if they'd installed 0.68.3 or 4 or something like that. Light LLM use Trivy in their GitHub. So 2 or 3 days later, they were attacked by the same, or they were compromised by the credentials which were harvested at the first attack. light LLM is important because a lot of companies use it to sit between their internal systems and a lot of the LLM providers out there. Allows you to pick and choose which LLM you're going to use for which purpose. But if that's compromised, it's seeing all of the tokens. It's seeing what you're sending to these LLMs. It's got your internal secrets as well, which they then exfiltrated and went on to the next target. So you're seeing supply chain attacks on LLMs-based systems as well, which is makes life a lot harder. What's interesting with light LLM is that it meets all three properties of the lethal trifecta, but it's meant to, by its very kind of arrangement in the system, it's meant to have access to all of these things, and it got compromised. So you have to run these things at risk. They're very useful, but they're in the systems. People are designing platforms with them in there. Step back a bit into MCP. This is a popular one. Google Workspace is quite popular. There's a lot of tools in Google Workspace that if you're using that as a platform, one well-crafted email coming into your system can then mean they have access to everything. You can get lateral movement from Gmail into Drive, Google Drive, or Google Docs, or any of the contacts. Sorry, that's another diagram, the same kind of thing. But on the right there, you see, this is an example from some of you. She works at Facebook. I'm trying to remember what her role is, but she's a senior person at Facebook. She knows what she's doing when she talks to LLMs. She'd set up an OpenClaw system. I don't know if it was Google Workspace, but it was a similar thing where she'd given it access to her emails. It decided to delete her emails, and she couldn't stop it. These things are autonomous for a reason. With OpenClaw, that's what people want. You want that autonomy of action from the system, but there's dangers with it. This was a similar one, sorry. It's the same. This is a similar again, but called Please Fix. This was a zero-click agent hijack from Zenity Labs, where basically it's a calendar attack. They sent a calendar invite. It was received by an LLM. The LLM then decided to access the local systems and exfiltrate data. These are the same kind of calendar invites we've seen from phishing attacks for a long time. They look the same. On the top, it looks like a normal email, but at the bottom, there's all kinds of things which, in this instance, are only designed and meant to be seen by the LLM for it to see it, whether it's in one-point text or some funny font that humans can't see, but LLMs can, or even simply just white on white text. So this came out of research from Irregular Research, where agents like to be helpful. They want to do things for you. They're like a little puppy at times. The user said to this system, this file is critical. Don't ever let the backup fail. It started to try and back the file up, found it couldn't do it. So it found a way around that. Disabled Windows Defender, downloaded the file. It's pen testing itself. You're pen testing your internal system. There is another example where one agent managed to co-opt another agent into colluding with it, and they were exchanging data via some weird language that they decided over UDP again, exfiltrating data, but based on what the user wanted. MCPs are not the only way of talking to the system. There's skills as well. Our skill set depends. They still use tools. A lot of them still may use an MCP underneath, or they may use CLI tools. But they're more complex because they're obviously a prompt of their own, and how the prompt interacts with other prompts in the system is complex. That's a different talk. Perhaps I'll come back and talk about that again. Sorry, I talked about that. So 3 papers published this year from different institutions that, if you take them together, they form a complete threat model. Stanford's research showed that LLMs is obviously often unfaithful. It gives you the right answer. It's a fabricated explanation as to why it gave you that answer. And then, because we're putting so much trust in these models, they're training us to make a fake decision based on information they've given us. Irregularly, we briefly touched on them before, but if you give these tools which are unreliable and that you give them urgency, they can go offensive. There's no attacker needed. The Cambridge paper shows that once the agents are autonomous, the human control doesn't gradually fade, it just collapses, like we saw with the email here. You can see in the conversation where she's saying stop, and the agent's ignoring her. It's already gone into its mode where it's just acting. So we're deploying these systems that they pass benchmarks. It fails so silently in production. They go offensive when they hit friction, and they resist correction when we try to stop them. And the reason that they show us to explain all this and justify their actions can be fabricated. So there are a number of things you can try here. One is process isolation, containers, visors, VMs. You can manage your credentials through different techniques. And then there's agentic permissions, scoped auth, approval gates, least privilege. And this is where there's least research in the field, it seems. Most of the industry research is on the other side of things. Firecracker, for instance, is what Amazon use underneath their Lambda platform. But OpenClaw, all of the OpenClaw incidents happened within authorized permissions. They didn't do things they weren't supposed to do. They were just given overly broad permissions, or in some instances. The Cambridge AI Safety Hub have come up with this kind of concept score where you try to understand your risk based on the minimum score of each of these dimensions here. And by what they're trying to do is apply the restrictions outside of the LLM itself. It doesn't know it's being restricted, but the restrictions are there nonetheless. I'm sure those of you who have used Claude Code have seen this, where, hey, can I do this? And you get bored of answering the same question. So eventually you say, yeah, always do it. Same as with some of the phishing attacks where they hammer on your OAuth, your 2FA, or MFA, constantly try and get you to say, yes, let me in. And eventually you give up because you're bored of putting it on your phone or whatever device and saying yes. So there's a few things I think we can do here. One is you can have read-only agents. So only 2 of the trifecta. You can put them in sandboxes. which works up to a point, but sandboxes are hard to manage, maintain, and run. And they add additional complexity that your average user on the street won't put up with. And you can gate your output, look at what's going on, what was coming out your LLM or your system, coming out the other end. And that's where your DLP management, we saw a talk earlier about Microsoft Purview. That's where those kind of things can help. But the safeguards inside the LLM may not work. A system prompt that says never reveal secrets is not, it's not a security control. It's a suggestion to the LLM. There are ways of doing it, but it's not 100% guaranteed. I think that the boundaries have to be at the tool layer. It's not on the LLM. It's how you what the LLM is calling to and around it. So maybe this is the takeaway. You've seen the lethal trifecta. Do these things. List every system that you've got that has AI access. Which is AI and has tool access. Understand those three properties we talked about at the start of the talk and how they apply to that particular system or agent. If any have all three, those are the ones to look at first. If they do have all three, is there a way of building an agent so it doesn't have all three? Do you need that one agent? Is it the one agent needs to rule them all? Or could you compose your agents out of different fragments to give you the same system, but where you can reason a bit more easily about the component? And if you can't, what is your blast radius? What happens if that agent goes rogue? What is going to happen? As I said at the start, when I submitted this talk, I thought it was just going to talk about how to attack the systems, how to attack the LLMs. But the landscape is moving really, really quickly. OpenClaw came in and changed the world, changed the landscape quite significantly. You can see Anthropic is now putting features into Claude and the desktop version that mirror some of those features that we saw in OpenClaw. OpenClaw was open source. You at least could see what it was doing. Didn't have any security constraints. But there's Claudes. The ones they're releasing have these constraints, or are they just trying to play catch up? But the security basics don't change. You have to understand what's in the environment. You have to know what things are being used by who, by what are they doing, and how is it being used. You have to patch your systems. The light LLM issues saw that. There's a bunch of systems probably still out there now running compromised versions of light LLM. And then you have to protect your system. But don't forget, LLMs are not magic. They're just bits of software. They're very good. They seem like they're human, but they're not. So secure them like software. The landscape may have changed fundamentally, but fundamentals didn't. I'm sure you all know how to secure it. Just go and do it. Questions?